Welcome to this lecture of the ongoing series of lectures in linear algebra. Today we'll be starting a new module and let us briefly recall what we did the last time. So last time we defined the notion of the transpose of a linear map. So suppose we have a linear map from a vector space V to W. Then we defined the transpose of T as a linear map from the dual of W to the dual of V as follows. So given a member of the dual of W, we defined this in a certain way, which is equivalent to expressing it via this following diagram. So we have G as a functional on W. Then to obtain T transpose G, what we do is we just compose it by T. So we get a linear map from V to F, and that linear map is what we call the T transpose G. So in other words, T transpose G is just the composition of T with G. And in the previous lecture I did not state it this way, and somehow it just slipped my mind to mention this diagram, which would have clarified things a lot if I had done that. So let's take a note of it, that this is really the definition of transpose, no different than what I said the last time. Then we saw some properties of transpose. We saw that the kernel of the transpose can be expressed in a very nice way in terms of the annihilator or the image of T, and we have a similar formula for the image of the transpose. And one thing I did not mention the last time was that this implies that rank of T transpose is same as rank of T. So to do this, just take the dimension of both the sides and apply the dimension annihilator theorem to this. So we get that. And then we saw this very nice commutative diagrams to commutative diagrams property of transpose. So if we have a diagram in the world of vector spaces, so these are linear maps and we have this composite so that this diagram commutes, then we obtain another linear map, then we obtain another diagram again in the world of vector spaces such that the arrows get reversed and things get decorated by their duals. So the linear maps become their transposes and the vector spaces become their duals. So that's it. And then we saw this identification between the double dual of a map and the original map itself via these natural isomorphisms between the duals of the vector spaces. And everything that I want to say is already written in this diagram. This diagram commutes is all that I would like to say in that regard. We discussed this at length the last time. Alright, so now for the problems for today. 3 problems, and we have a new definition here which is used in this problem. So just take a note of that. Okay, and now let's move on to the material of this lecture. And before we start with the definitions that are pertinent to this lecture, we recall a very simple fact that we proved long ago. Is that suppose we have a linear endomorphism, then these 3 statements are equivalent. So the first statement is that the map is injective. The second is that the map is surjective, and the third is that the map is bijective, which is another way to say that it is an isomorphism. Why are these 3 statements equivalent? Just apply the rank nullity theorem and you will get this. And one piece of definition I would like to, or rather terminology I'd like to mention, is that isomorphisms are also called invertible maps. Linear isomorphisms, a linear map from a vector space to another vector space. Suppose we have been given such a map, then we'll call this an invertible map if and only if it is an isomorphism. So it's just a terminology. This is not a new concept. Okay, and now let's get to the business of eigenvalues and eigenvectors, which is the subject of inquiry for this particular lecture and perhaps the next lecture. And it will be a central concept throughout our linear algebra study. Okay, so here is how we define an eigenvalue. So first of all, we have a linear endomorphism. So let T be a linear endomorphism we say that a scalar lambda in F is an eigenvalue of T if there exists a non-zero vector V in the vector space such that TV equals lambda V. So please take note of this non-zeroness, it's very important. So let me also highlight the definition that we are making. So we have defined the notion of an eigenvalue, and let's see what we are trying to actually capture. So suppose I have a vector space, which of course the best I can do is think in R2. So suppose we have a vector space. I mean, of course, as a figure I'm drawing R2, but we have to convince ourselves that we are actually talking in general. So this is just, of course, a pictorial way to think about things. So suppose we have vector V, which when we hit by T, we get some vector which is in the same line along V. So let me draw this picture once more. So suppose we find that after we hit this vector by T, we obtain possibly a longer or shorter vector, but it's in the same line as V, meaning it's in the same one-dimensional linear subspace that is spanned by V. So then this scaling factor that we obtain, which could be 1, it could also be 0, that is what we call an eigenvalue. So it has to do with the invariance of one-dimensional subspaces. If you have found, suppose you have a linear endomorphism and you have found a one-dimensional T-invariant linear subspace, then that linear subspace will furnish an eigenvalue. Just pick a vector in that subspace, just pick a non-zero vector in that one-dimensional T-invariant subspace and hit it with T and obtain the scaling factor. That scaling factor is an eigenvalue. So that's the definition. Note that lambda in F is an eigenvalue of T if and only if the kernel of this linear operator is not the trivial subspace. So this linear operator is of course, when I say linear operator, I mean a linear endomorphism. Operator and endomorphism are the same things. Let me make that comment here. So this is also known as operators. So what is this? What do I mean by T minus lambda I? So I mean, we have already noted this, that the space of all linear maps between two vector spaces is again a vector space where we add things and scale things in the natural way. So we already know what this means, but let me still say explicitly what does it do to a vector. So if I have a vector V in our vector space capital V, then this produces TV minus lambda V. That's the output it gives. I is the identity transformation. It doesn't change anything. So this is self-explanatory, this statement. I don't think I can say much about it. So just note this. This is the case. And therefore, by what we recalled here, we see the simple fact that lambda in f is an eigenvalue of t, if and only if t minus lambda I is not injective, if and only if t minus lambda I is not surjective, if and only if t minus lambda I is not bijective. Or let me say is not invertible. That's a better way to say it. Is not invertible. So all of this is, there's nothing very difficult about this. So just one comment I would like to emphasize, that 0 can be an eigenvalue. There's nothing wrong with it. It's perfectly fine to have 0 as an eigenvalue. Okay, so now let me define what is an eigenvector. So here is how we define eigenvectors. So let T be a linear operator or linear endomorphism. And lambda be an eigenvalue of T. So we say that V in capital V is an eigenvector corresponding to lambda if TV equals lambda V. Alright, so just a vector which witnesses this scaling, and this is allowed to be 0. 0 is allowed to be an eigenvector. However, some authors may not do so. Some authors may always disregard 0 as an eigenvector. So that depends on really the author. But I personally like to regard 0 as eigenvectors. So in other words, the set of eigenvectors corresponding to an eigenvalue lambda of T is nothing but the kernel of t minus lambda I. That's precisely the set of eigenvectors of an eigenvalue lambda. Another thing to note is if V is an eigenvector, if V is a non-zero eigenvector, let's say if V is a non-zero eigenvector, or let me make a better statement. A non-zero vector is an eigenvector corresponding to some eigenvalue if and only if span of the vector is T invariant. Again, this is very easy to prove just by the definition of an eigenvector. So non-zero eigenvectors are precisely those vectors which span an invariant subspace. So if you have a one-dimensional invariant subspace, just pick any non-zero vector in that and you have found an eigenvector. In fact, you can pick any zero. The zero vector is also an eigenvector in that case. But I would like to emphasize this only for non-zero vectors. Alright, so the notion of a one-dimensional invariant subspace is very tightly linked to the notion of eigenvalues. And we'll make use of this simple observation many times later. So just let me put this as a remark. So this is a one-dimensional subspace because the vector is supposed to be non-zero. Alright, so that's eigenvectors. Now let's see an example that one could ask the question, do eigenvalues always exist? Suppose I have a linear endomorphism. Can we always say that there is at least one eigenvalue of this endomorphism? And this example shows that no, that is not the case. So consider this real vector space R2, and we have a linear endomorphism defined in this way. So E1 is this vector, and E2 is this vector, the standard basis vectors. And the linear endomorphism is defined via sending E1 to E2 and E2 to minus E1. So this goes here and this goes here. So if you work out, of course then the actual description is this. The linearity forces that T behaves this way. And if you work out what exactly T is doing to an arbitrary vector is the following. So suppose you pick an arbitrary vector in R2, then T is just rotating this vector by 90 degrees. So if this is a vector V, then just 90 degree rotation of that is the vector TV. So T does not have any eigenvectors because there is no one-dimensional T invariant subspace, since whenever you pick a one-dimensional subspace and apply T to it, you get something perpendicular to it. So there is no one-dimensional T invariant subspace, and therefore T cannot have an eigenvalue. The operator T does not have an eigenvalue. Because if it had an eigenvalue, it would have an eigenvector, and therefore it would have a one-dimensional T invariant subspace, which it does not. Okay, so then the question is, can we is there some hypothesis under which one can guarantee that T indeed has an eigenvalue? And yes, there is such a hypothesis, but before we get to it, we need to, let's say, I mean, it's not completely necessary, but it is a good idea to discuss this because it's a very convenient notation. So let F be a field, and of course you can think of F as R or C if you like. So F is a field. We write Fx to denote the set of all polynomials over F. So recall that our notation F sub nx denoted the set of all polynomials over F of degree at most n, but this notation is all polynomials, no constraint on the degree of the polynomial. So that's just one notation. Now let T be an endomorphism. So we have a linear endomorphism, and V is a vector space over F. So that is something that I won't write. So the base field of V is F. Now for a polynomial, Px equals a0 plus a1x plus dot 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 an x to the n. So just some polynomial over F. We write P bracket T to mean the linear endomorphism. a0 plus a1t plus dot 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 an t to the n. So this is an endomorphism on V. Note, this is an endomorphism on V because T is an endomorphism on V. You just composed it n times. Of course, this is an endomorphism. All of these are endomorphisms over T. So yeah, one thing I should mention, that when we write a0, we really mean a0 and identity. So this is t to the power 0. You can think of it as t to the power 0, but the correct thing to write is really identity. Many times one may just skip this and it is kind of understood that it is present here, but I would like to always write it. Sometimes I might slip, but anyway. So we write pt to mean this guy, where this guy is an endomorphism because it is a linear combination of endomorphisms. All of these are endomorphisms of V, and these are just scalars by which we have scaled them and then we have added them. So out of any polynomial we obtain another endomorphism using one fixed endomorphism. So this is just a notation. There is nothing very deep going on, but a few things we can note is that if Px and Qx are polynomials, then Pt composed with Qt is equal to Qt composed with Pt, which is nothing but Rt, where Rx is the product of Px and Qx. So one can multiply polynomials. I'm sure we know the multiplication of polynomials from high school, so it's just the same definition. And we have this nice looking I mean, all I'm saying is that this notation behaves very well with the usual operations of polynomial multiplication and addition that we've been familiar with since our high school. And many times we will not even write this composition symbol. We'll just simply write PTQT. So whenever we have two endomorphisms, we write ST to mean S composed with T. So just a matter of notation. So PTQT may be just PT composed QT may be written as just PTQT. There's nothing very interesting going on here. Okay, so just very simple notational things. And now let us look at how to go about proving the complex eigenvalue business. So we need a result from algebra which says the following. So let Px be in this set. So we have all the polynomials over complex numbers, and we have just picked one of them. So if Px is non-constant, then there is a complex number alpha such that P alpha is 0. So let's say what we mean by non-constant. So for instance, if you take this polynomial, let's say 2, this is a legitimate polynomial over complex numbers. It's just like, I mean, these guys are polynomials, right? Anything of this sort is a polynomial over complex numbers, where of course all of these are complex numbers. So when we write, let's say 2, we just mean that only this part is non-zero and all of these guys are 0. So every complex number can be thought of as a polynomial over complex numbers. Every element of a field can be thought of as a polynomial over that field. And clearly, if you consider such a polynomial, then this cannot happen. Well, first I have to say what I mean by this notation. So if we have a polynomial, let's say this is my polynomial Px, then by P alpha we mean this complex number, which is obtained by substituting alpha for x. This is a complex number because this is a complex number, all of these are complex numbers, we multiplied them and added them. So this is the evaluation of P at alpha. I'm sure we are familiar with this kind of thing. So clearly this kind of polynomial cannot have a alpha which satisfies this equation, because no matter what alpha you feed into this polynomial, you retain the same answer. But as soon as you have some other polynomial, the theorem says that there is an alpha which satisfies this, and such an alpha is called a root. Let me erase this thing. In other words, every non-constant polynomial over C has a root. So a root of a polynomial is a scalar, meaning suppose your polynomial was over some field f, then a root of that polynomial is any member of that field, such that if you evaluate the polynomial on that scalar, then you obtain 0. Any such thing is called a root. And the fundamental theorem of algebra says that every non-constant polynomial over complex numbers has a root. And the above is of course not true. Is not true if we replace C by R. So not every non-constant real polynomial has a root. So for example, x square plus 1, when thought of as a polynomial over real numbers, does not have a real root. Because no matter what real number we plug in place of x, we will always obtain a positive real. So of course this cannot become 0. But it of course has a complex root, namely iota. So the fundamental theorem of algebra crucially requires the complex number field and not the real number field. Okay, so now we'll use this theorem to prove that every complex linear endomorphism has an eigenvalue. So here is the theorem. Let V be a complex vector space. And let's say the dimension of V is at least 1. Otherwise it's anyway not interesting. So we have a non-trivial complex vector space. Let T be a endomorphism. Then our statement is T has an eigenvalue. And this is what we want to prove. Okay, and the proof is quite interesting. It's not an obvious kind of proof, but yeah, I mean, once we see it, it kind of becomes natural. So we start with any non-zero vector. Let V in V be a non-zero vector. Such a vector exists because the dimension of V is at least 1. And consider, and let's say dimension of V is n. So let the dimension of V be equal to 1. No, sorry, what am I saying? The dimension of V be equal to n. It's some n dimensional space, and of course it's some positive integer. So then consider the vectors V TV dot 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 T to the nV. All of these are vectors in V. And how many of them are there? There are n plus 1 of them. A total of n plus 1 vectors. So these cannot be linearly independent. Simply because the dimension of V was n and we have n plus 1 vectors here. So we cannot find a linearly independent list of size more than n. And therefore, there exist scalars, meaning there exist complex numbers in C, not all of which are 0, such that the linear combination vanishes. Okay, and now we'll use polynomials. So define Px, a polynomial over C, as Px equals alpha 0 plus alpha 1x plus dot 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 alpha n x to the n. And this is a non-zero polynomial because not all of them are 0. In fact, this is a non-constant polynomial. Note that Px is non-constant. Because if it were a constant polynomial, that would mean that all of these are 0. Alpha 1, alpha 2 up to alpha n, they are all 0. But then what would this equation give us? This equation would say that, well, all of them are already 0, and the fact that this is 0 means that alpha naught must also vanish, because the vector v is non-zero. So if a scale of a non-zero vector vanishes, then the scalar is 0. But that would mean that all of these alpha i's are 0, but that is contrary to the inference that not all of these alpha i's are 0. There is a non-trivial linear combination of these vectors which furnishes 0. Alright, so that's why Px is a non-constant polynomial. And let me label this equation as star. And star says nothing but the equation star is precisely saying that Pt, as we discussed what this means, operated on V is 0. That's a very neat way of writing this whole thing. And now by fundamental theorem of algebra, there is a root lambda of Px. So if a polynomial has a root, then suppose lambda is the root of Px, then you can show that Px is of this form for some polynomial Qx. This is like division with remainder. So if you take this as a divisor of this polynomial, you get some remainder whose degree is less than this guy. So the remainder is some constant, meaning some complex number, beta, let's say. But then if you substitute lambda on both sides of this equation, this thing vanishes, and therefore beta must be 0. So that's that. I mean, if you have a root, then the linear polynomial coming from the root divides the polynomial whose root is lambda. That's a very, again, I'm sure we are familiar with such a thing from high school. It's called the factor theorem or something. Anyway. Yeah. So now, since we have PTV equals 0, we get T minus lambda I QT V equals 0. So we just use the fact that PT is nothing but T substituted here composed with T substituted here, and that is what we have written. When you substitute T here, you get T minus lambda I, and when you substitute T here, you get QT. And as we discussed that product and composites, they behave well and all of that, thing that we said. When you substitute t here, you get this, where there is a hidden composition sign here which we do not write. Now there are two possibilities. So if lambda is an eigenvalue of t, why am I writing it here? If lambda is an eigenvalue of t, then we are done. So we may assume that lambda is not an eigenvalue. But then t minus lambda I is invertible. So this equation t minus lambda I composed with qtv equals 0 implies that qtv equals 0, because this is an invertible linear operator which has been fed this vector qtv and it is producing 0. But if an invertible linear operator produces 0 on a vector, that vector must itself be 0. So we get this is 0. And now we can reapply the same thing that we did. Whatever we did to px, now we can do to qx. Our leverage was this equation, that ptv equals 0, and then we were able to do this business. And we obtained a polynomial of smaller degree which satisfies the same equation. So we can keep doing this unless either we at some point find an eigenvalue, or we will halt at this kind of an equation. Ultimately, if we fail to find an eigenvalue, then at some point we will see an equation of this sort, that t minus maybe I shouldn't say lambda, maybe mu I of v equals 0. Basically, what I'm trying to say is that ultimately we would land up with a degree 1 polynomial q which satisfies this equation. Assuming on the way we never found an eigenvalue. I mean, whenever we found a root of the polynomial, that root was not an eigenvalue. And if this keeps on going, ultimately we will end up with a polynomial which is of degree 1, and hence we would have an equation like this. But that would mean that this particular thing is an eigenvalue. So that's the proof. I mean, writing all that is not going to clarify anything. And therefore, I mean, I'm skipping all those steps. Maybe you can fill it for yourself. Therefore, t has an eigenvalue. So we crucially use the fact that we are working over complex numbers, because we wouldn't have this facility otherwise. If you know about algebraically closed fields, then you can see that the same proof goes for any algebraically closed field. The only property of complex numbers we have used is precisely that it is algebraically closed, nothing else. But anyway, we don't need to know about algebraically closed fields. So that's a very nice fact about complex endomorphisms. Okay, so this is all that I wanted to discuss for this lecture. As usual, like, comment, share, subscribe. Support me on Patreon, the link in the description below. And I'll see you next time. Thank you.